Welcome to the deep dive. Today we're really digging into a pretty fundamental challenge for large language models. How do you get them to handle really long stretches of text without, well, falling over?
Right.
Because the classic transformer architecture, the one that started it all, it hits a kind of computational wall with long sequences. It's all down to that self-attention mechanism.
Exactly. That's the core bottleneck.
We have seen some promising approaches, models with linear scaling like RWKV, but even they've had limitations with truly long contexts.
Yeah, the problem with the standard transformer, the original kind, is that self-attention. As the text length, let's call it n, grows, the compute needed just explodes. It goes up with n squared, n2,
N squared, so every word basically has to check in with every single other word.
pretty much, which is amazing for understanding relationships in, say, a sentence or a paragraph. Super powerful.
But scale that up to a novel or, huge technical docs.
And it becomes computationally prohibitive. Just eats up resources, processing power, memory, you name it. It's a massive drain.
Okay, so that's the quadratic bottleneck. Then we started seeing these linear complexity models pop up where the cost scales more gently, just ON.
Right. Things like linear attention, state space models, Mamba is a big one there, and linear RNNs, which is where RWKV and DeltaNet fit in.
And the big advantage there is efficiency, right? Especially for inference, like when the model's actually generating text.
Precisely. These linear models find ways around that all pairs comparison. Maybe they process sequentially, keeping an internal state, like an RNN. It fundamentally cuts down the work needed for those long sequences, making them much more practical for, real world stuff involving long documents.
Now, RWKV itself, it's not static. It's been evolving, hasn't it? We've had RWKV4, -5, -6, -7. What's the story there? What's been changing?
Well, RWKV was interesting from the start because it's a hybrid. It kind of blends ideas from transformers and recurrent neural networks, RNNs.
Okay.
So it gets that linear complexity, which is great, but it can still be parallelized during training. That's a big win from the transformer side. And it has that recurrent state, like an RNN, which is efficient for sequences.
And the different versions improved on that.
Yeah, each one built on the last. RWKV5 brought in more complex states, a more dynamic recurrence. RWKV6 was about making training more stable, allowing for bigger models.
Yeah.
And then RWKV7, the immediate predecessor to what we're talking about today, introduced dynamic state evolution. That really boosted its ability to learn on the fly from the input text, what we call in-context learning.
Okay, so that brings us to the main event, RWKV-X. What's the X all about? What makes this one different?
The X is the big architectural twist here. It's another hybrid, but this time it combines those established RWKV7 blocks with something new, sparse attention blocks.
Sparse attention, okay.
Yeah, the core idea is smart. Use the efficient RWKV part for the nearby stuff, the short-range dependencies in the text, words close together, and then bring in sparse attention specifically to handle the long-range connections, the context that stretches across a really long document. Figure 2 in the paper actually shows this layered structure pretty clearly.
So it's like specializing RWKV for local, sparse attention for global. Kind of the best of both worlds.
That's the goal, exactly. Leverage the strengths of each.
All right, let's get into this sparse attention then. The paper calls it top K chunk sparse attention. Sounds specific. How does that mechanism actually work? What's novel there?
Okay, let's break that down. First, they divide the whole input text into smaller pieces or chunks, manageable segments.
Right.
Then, when the model is looking at one chunk, the query, it doesn't try to compare it to every other chunk. That would defeat the purpose. Instead, it calculates a relevant score between the current query chunk and all the other chunks. Equations 4 and 5 in a paper show the math behind that scoring.
So it figures out which other chunks are likely important.
Precisely. And based on those scores, it selects only the top K most relevant ones. K is just a small fixed number.
Okay.
Then the actual attention calculation, the heavy lifting is only done between the query and those chosen top K chunks. Equation 6 shows that limited calculation. This selective focus is what gives you the huge efficiency gain over standard attention, which looks everywhere.
That sounds, incredibly efficient. Instead of all to all, it's just all to a few important ones. What does that do to the complexity, the ON stuff?
It makes a massive difference. During training, this top K chunk approach brings the complexity down to OKDN. Now, K is the number of chunks selected, B is the chunk size.
Both small, fixed numbers.
Exactly. So since K and B are constants, the overall complexity essentially becomes linear with the sequence length n. It approaches ON.
Wow.
And maybe even more aggressively, during decoding, when it's generating text, the cost per new token becomes ON double. Constant time. It doesn't get slower as the text gets longer. 0.001 per token, regardless of how much text came before.
That's the idea. Table 1 in the paper lays out these comparisons nicely. It's a fundamental shift in maintaining speed, even with enormous contexts.
Okay, that's a huge deal for inference. But speaking of long context and inference, there's always the issue of the KV cache, right? As you generate text, that cache of keys and values keeps growing. How does RWKV-X handle that? That can become a memory nightmare. Absolutely, that's another critical piece, and RWKV-X has a really neat solution, inspired by something called SnapKV. The goal is to keep the cache size fixed, constant, no matter how long the sequence gets.
Fixed size? How?
Well, conceptually, they split the cache. You've got the older stuff, the accumulated past dates, and then a more recent observation window, the stuff the model just saw or generated. Figure 7 gives a good visual for this.
Okay, so long-term memory and short-term focus, kind of. Then what?
Then they calculate an importance score for the items in that older cache. This score is based on how much attention they get from the recent observation window. Equation 7 details how that's calculated.
So the recent context tells you what's still relevant from the distant past.
Exactly. And based on these scores, it keeps only the top most important keys and values from that old cache M is like your fixed memory budget.
Ah, I see.
It takes those top important old items and combines them with everything from the recent observation window. This creates a new, updated cache that's still the same fixed size, but represents a condensed version of the entire history. It stops the memory use from just growing and growing.
That is clever. It's like intelligent compression for the model's memory. Okay, so we have this efficient architecture, smart cache management. How do you actually train RWKV7? You mentioned it builds on RWKV7, so it's not from scratch.
Correct. They use a technique called block expansion, which drew inspiration from Llama Pro. Instead of starting totally fresh with random weights, they essentially insert the new sparse attention blocks into a pre-trained RWKV7 model.
Minimizes random initialization, helps transfer knowledge.
Exactly. More stable, more efficient training. And the training itself happens in two main stages.
Okay, what are those stages?
First is what they call alignment pre-training. Here, they train on relatively short text sequences, 1024 tokens from the minipile dataset. And crucially, during this phase, the original RWKV7 blocks are frozen. Their parameters don't change.
So you're only training the new sparse attention blocks.
Right, letting them learn how to work with the existing RWKV blocks. Then comes stage 2, long context continual pre-training.
Longer texts now.
Much longer. They use the prolonged 64K dataset that's a 64,000 token context length, a billion tokens total. And now all the parameters are unfrozen. Everything gets trained together, the original RWKV parts and the new sparse attention parts. This is where it learns to handle those really long-range dependencies.
And I read something about a special loss function to help with the long context learning.
Yes, that's another key innovation. The long context cross entropy loss, or long CE. It's a modification of the standard loss function used in training language models.
How does it work?
It dynamically adjusts the importance, or the weight, given to each token during training. Tokens that the standard loss function suggests are particularly important for understanding the long-range context, maybe surprising words or key pieces of information, get a higher weight, greater than 1. Less critical tokens get a weight closer to 1. So it essentially tells the model, hey, pay extra attention here. This part is really important for figuring out the big picture across this whole long document. It helps focus the learning.
Like highlighting the crucial clues in a mystery novel for the model. Okay, so cool architecture, clever training. Does it actually work? How did they evaluate RWKV-X's performance?
They looked at it pretty thoroughly, both long context abilities and general short context performance, plus efficiency. For the long stuff, they use the single needle in a haystack benchmark.
The find the hidden sentences test.
Basically, yeah. Can the model find a specific piece of info hidden deep inside a very long text? Table 2 and Figure 1 in the paper show the results. RWKV-X did significantly better than RWKV7 and other models, especially on the harder versions SNIH2 and Native 3.
Harder versions require more reasoning?
Right, not just finding the needle, but maybe understanding something about it in context. So RWKV-X showed stronger capabilities there.
Okay, so it's good at the long context party trick, but did optimizing for that hurt its everyday language skills on shorter texts?
That's always a concern, but Table 3 shows the results on standard short context benchmarks. And the takeaway is that RWKV-X holds its own. It's competitive with the previous RWKV versions and other baseline models, even larger ones sometimes.
So we didn't sacrifice general ability.
Doesn't seem like it. The changes made for long context didn't break its performance on standard tasks. It's still a solid general-purpose LLM.
Good to know. Now, efficiency was a big promise. What do the numbers show there? How does it stack up speed-wise?
The efficiency analysis is quite revealing. Figures 3, 4, and 6 plus Table 8 have the details. Figure 3 looks at pre-fill latency, how long it takes to process the initial prompt.
Okay.
And while maybe a super-optimized full-attention transformer like Flash Attention v3 might be a tiny bit faster on very short prompts, as the sequence length grows, RWKV-X pulls ahead. It shows significant speedups because of that near-linear scaling.
Makes sense. What about generating text, the decoding part?
That's figure 4. And it's really striking. RWKV-X shows incredibly stable decoding latency. The time to generate each new word stays pretty much constant, even when the context is enormous, up to 1 million tokens in their tests.
1 million tokens, wow. And the speed stays flat.
Yeah, that's the fixed size KV cache paying off. Now, vanilla RWKV7 might actually be slightly faster in absolute terms on shorter contexts.
But RWKV-X maintains its speed at extreme lengths.
Exactly. That stability at scale is huge for practical applications with massive texts. And figure 6 also shows it's generally more computationally efficient during training compared to RWKV7 across different sequence lengths.
Okay, impressive gains, especially at those crazy lengths. The paper also did some ablation studies, right? Taking parts away to see what matters.
Yep, those are always insightful. They look at a few things. The long C loss, for instance, Table 4, shows that taking it away really hurt performance on the long context tasks. So that dynamic weighting is pretty crucial.
Right. What else?
They tested different ratios of RWKV blocks to sparse attention blocks. Figure 5 suggests a sweet spot around 25% sparse attention layers. That mix gave the best validation loss, suggesting it's a good balance between RWKV's efficiency and sparse attention's long-range power.
Interesting. So not all sparse attention, not all RWKV, but a specific blend.
Seems that way. They also compared scaling to GPT-2 in Table 5. RWKV-X showed better scaling behavior. It seemed to use its parameters more effectively as the model size increased.
And wasn't there something surprising about positional encoding?
Yeah, that was interesting. Table 6 showed that adding explicit positional encodings, the standard way transformers know where words are in a sequence, had minimal impact on RWKV-X.
Really? How does it know word order then?
The thinking is that the inherent recurrence in the RWKV architecture itself already provides enough sequential information. The model figures out the order from the way it processes the sequence step by step.
Fascinating. So, okay, let's try and wrap our heads around this. RWKV-X is this hybrid model, RWKV7 plus this novel top K chunk sparse attention.
Right.
Giving it near linear training complexity, ON, and constant inference complexity, ON, per token, thanks also to that clever fixed size KV cache.
You got it.
And it performs well on both super long context tasks and standard short ones, while being more efficient than older RWKVs and traditional transformers, especially at scale.
That's a great summary. The hybrid design, the specific sparse attention mechanism, and the cache management, those are the core innovations driving the benefits.
Now, no research is perfect. Did they mention any limitations or areas where RWKV-X could still be improved?
They did. They pointed out a couple of things. One is that the way it selects the top K chunks for sparse attention is still a bit heuristic. It's based on scores, but maybe not always picking the absolute most semantically relevant chunks across the whole document. There's potential for more intelligent selection there.
Okay, make the chunk selection smarter.
Right. And the other point was about speed. While the overall complexity is great, the actual implementation of the sparse attention decoding part is currently a bit slower than the decoding in vanilla RWKV. So some engineering work, further optimization, could potentially make inference even faster.
Makes sense. Room for refinement. Well, this has been really insightful. RWKV-X definitely feels like a significant step in cracking that long context nut for LLMs.
It really does.
It opens up possibilities, doesn't it? When models can efficiently process and understand truly vast amounts of text. What new applications does that enable? What questions does this kind of advancement raise for you looking ahead?
Oh, definitely. It really highlights the power of combining architectural ideas. It makes me wonder, what other hybrids are possible? Could we see even smarter sparse attention? Maybe attention that adapts based on the content itself? And that finding about positional encoding, maybe we can simplify models further. It's clear the quest for efficient, powerful, long context understanding is far from over, and RWKV-X is a really compelling path forward in that journey.